Hey guys, how you doing? So welcome to the second video for this unit on kinematics, which looks at acceleration. Okay, so in this video we're going to take a look at what acceleration is, how do we apply the acceleration formula, and how do we understand the different kinematic formulas involved in acceleration. So let's jump into it. Okay, acceleration. Now, you'll notice here that once again the formulas are at the top, that they've been rearranged, and I have written the formula in red with the different aspects. Okay, defined as the change in velocity over time. Yeah, so acceleration looks at how much objects are changing their velocity over a given amount of time. Okay, the formula is A equals to delta V over T. A for acceleration is written in meters per second or meters per second squared, and I'll come back to that. Delta V, or change in velocity, is listed as meters per second to the power of -1, and then time in seconds. Yeah. Now, what that means is that the acceleration tells us whether an object is actually gaining velocity, how much it's actually speeding up. So not only is it moving, but every second that goes by, it moves faster, right? And so deceleration, on the other hand, tells us how much the object is losing speed and how much the object is slowing down. Okay, so if an object is speeding up, it must be accelerating, and if it's slowing down, it must be decelerating. Okay, because it's changing the speed that it's moving at. Okay, like velocity, acceleration is a vector quantity, which means it contains both magnitude and direction. Okay. Now, before we move on, let me just address this little unit that you'll notice here. Yeah. So if velocity is measured as meters per second, and then seconds is the measurement for time here, then acceleration is meters per second divided by seconds, or if you calculate it, it works out to be meters per second squared. Now, I won't go into detail how we get this meters per second squared, but the main idea is that in order for you to understand that meters per second squared is the unit for acceleration, whereas meters per second is the unit for velocity. Okay. Now, I've rearranged the formulas up here, so you can go ahead and use those formulas and work it out yourself. But let's go through a few work examples. Okay. Like velocity, nothing ever accelerates at a completely uniform rate. It kind of changes bits and pieces here and there. So what we do is instead we look at the average acceleration rather than the instantaneous acceleration, even though you can calculate instantaneous acceleration. Okay, so pause the video, have a go at these three questions, and then we will go through the solutions for them. Okay, all right, so let's take a look at the first question. A bike was stationary at the lights, accelerates to 36 kilometers per hour after 15 seconds. What is the bike's acceleration? So in this example here, the bike was stationary. If it's stationary, it gives us a really important clue. If you ever hear a question saying that the object is at rest or it's stationary, it means that the starting speed that it was going at was 0 kilometers an hour, which means that the object was not moving at the start, and then the change in velocity is 36 kilometers per hour. Okay, so the acceleration, how do we calculate that? Well, the first thing we have to do is we got to convert 36 kilometers per hour into meters per second, because the final unit for acceleration is meters per second squared. So I'm going to convert 36 divided by 3.6, which gives us 10 meters per second squared. 10 meters per second for the velocity, and then I will simply divide the velocity by the time. So it changed 10 meters per second in 15 seconds, which works out to be 0.67 meters per second squared. So the bike was gaining 0.6 meters per second in speed every second. Okay. Question 2, a car is traveling in a 40 kilometer zone, passes through a 60 kilometer zone. If it takes 4 seconds to reach the new speed, what is the car's acceleration? Now you will notice here that the object is not at rest. It was already cruising at a consistent 40 kilometers per hour, and then it changes to 60 kilometers per hour within 4 seconds. So now the change in velocity is actually 20 kilometers per hour. And remember, once again, because the final unit is in meters per second squared and the original units were in kilometers per hour, you have to convert kilometers per hour into meters per second first. So 20 kilometers per hour, which is the change in velocity, divided by 3.6 will give you 5.5 meters per second squared. So that's the unit for velocity that we want in meters per second, okay? So 5.5 meters per second in 4 seconds, right, so divided by 4, will give us 1.39 meters per second squared. So what that means is from the time that the car passes through the 40 kilometer zone that it was going at, it will gain 1.39 meters per second every second in speed until it reaches 60 kilometers per hour in the new zone. And it takes 4 seconds to do that, okay? All right, question number 3. A car is traveling at 50 kilometers when the driver suddenly hits the brakes after seeing ducks on the road. If the driver takes 4 seconds to stop, what is the car's acceleration? Okay, now the starting speed now is different. It is 50 kilometers per hour, so it's now slowing down because it is trying to brake. Okay, so 50 kilometers per hour, once again, needs to be converted into meters per second, which will give us 13.89 meters per second, right? And it takes 4 seconds to do that, so you take 13.89 meters per second divided by 4, which gives you 3.47 meters per second squared. Now, here's the catch. It is asking for the car's acceleration, right? But because the car is slowing down, the acceleration must be a negative value, yeah? So a car's acceleration must be negative value because it is slowing down. That negative tells you that the object is not gaining 3.47 meters per second every second. It's losing 3.47 meters per second every second, okay? So the official acceleration is negative 3.47 meters per second squared, or you can arguably say it is decelerating at a rate of 3.47 meters per second squared. So see what I've done there? Because I've used the word deceleration, you can say that it's lost speed at 3.47 meters per second squared. Okay, so that's kind of how we generally use the acceleration formula. If I was to show it in a graph, right, imagine acceleration being represented by something like, for example, gravity, because gravity is an acceleration factor, right? It causes things to accelerate. If an apple falls off the tree on the edge of a cliff, right, at time 0, the object actually hasn't moved yet, right? It's just broken off the tree and it hasn't moved yet. But if, for example, let's say gravity causes the apple to accelerate at 9.8 meters per second squared, what that means is after 1 second, the object has traveled 9.8 meters per second, okay? After 2 seconds, the object is now traveling at 9.8 meters per second times 2, which is 19.6 meters per second, right? And then at 3 seconds, it's 29.4, at 4 seconds, 39.2. Now, if you were to track the distance that the object travels, you will notice that the distance between each one gets higher and higher. So if you were to track distance, the distance would actually increase exponentially. It will gain distance at an exponential rate from the speed because it is gaining speed every second. Okay, so diagrammatically, when an object accelerates, you will notice that it covers more distance even faster than it covers more speed. Okay. All right. On a side note, I want to address this little symbol here, this idea of change, because you're going to see it with both velocity for displacement and for acceleration and velocity. Okay. So that symbol, that Greek symbol delta, represents change. When an object, when anything sort of changes, we use that little symbol, and it can easily be thought of what was it finally minus what was it initially. Yeah, so I'll give you a few examples. So in velocity, it was delta x, or change in position, can be thought of where the object's final position was minus from the initial position. Yeah. We can symbolically represent that by delta x is equal to xf in a subscript, that should be a subscript, minus xo, yeah? The f represents final, the o represents initial, okay? I know it sounds a bit funny, why doesn't it use an I? Sometimes it does, but most of the time it's 0 because it is at time 0, okay? So in acceleration, delta v can be thought of figuring out what the final velocity is, subtracting the initial velocity from that, which will give you Vf minus Vo, And so the acceleration formula actually has two different formulas. You've got this one here, delta v, or if you are given final and initial velocity, like one of the questions you had earlier, you can actually use that to calculate instead. So you had vf minus vo over t. Now, if an object is at rest, for example, like in our first question, VO usually is 0. So that's quite easy because then you can just use the final velocity that it reaches and divide it by the time it takes to do that. However, when an object is already traveling at a certain speed, you need to calculate what that change in speed would be before you can divide it by the time and figure out the acceleration of the object. Okay, so that's just a bit of an overview for delta V. Now this formula here is particularly useful, and you'll see in the next slide why that is, because sometimes delta V doesn't give us enough information. We need to figure out the final versus the initial velocity change. Okay, so here's an example of a complicated question. It seems simple at the surface, but it's very complicated, and it's hard to figure out if you just use these three formulas, and this is why acceleration is a very complicated formula. Okay, so a book on the ground was kicked forward with the initial velocity of 5 meters per second. So someone has kicked the book and it is traveling at 5 meters per second. After 3 seconds, the book had slid 8 meters. How do you calculate the acceleration or the deceleration of the book? Yeah. So this might seem like a very simple equation at the start, but the big problem you've got is actually you do not have the object's final velocity. Yeah, we're not saying that the object has stopped traveling after 3 seconds. We're saying what's it decelerating at after 3 seconds and covering 8 meters if we don't have the final velocity. Okay, so the final velocity is unknown. So here are the things that we do know, and here's the problem that we face. Okay, so the initial velocity, VO, is 5 meters per second, right? Time is 3 seconds, and the displacement is 8 meters per second. What is the acceleration? So notice here that we know how far it's gone, we know the time it takes to go that distance, and we know that the speed it was initially traveling at was about 5 meters per second. We don't know, however, what the final speed is, and we also don't know the acceleration rate. So what's interesting is that even though it looks like a simple question, it's actually very complicated because we have two unknown variables, and that's a big problem in calculating in mathematics. If you have only one equation but two unknown variables within the equation, you actually can't calculate either one of those variables because they can change, right? So we can't use this formula here, delta V over t, because we don't know what the final velocity is. So you can't minus the final velocity from the initial. If it was at rest, then we can, because it would be 0, but we don't know it. So you can't use either of these formulas, right? So the solution is we have to use a very complicated set of acceleration formulas that have been the same formula but rearranged like crazy to figure out the formulas. Now, this is a shortcut, yeah? If you were to rearrange these formulas yourself, it would be very complicated, but for the sake of this unit, what we're just showing you guys is the final product. How do we rearrange the formulas in such a way that we can figure out each one of those individual variables in the context of the other? Yeah. So what I've done now is I'm no longer using A equals to V over T, but rather I'm using the more specific formula A equals to Vf minus Vo over T. Yeah. Final velocity minus initial velocity over time. Now, this formula can be rearranged in 4 different ways, right, to give you T, Vf, and O. So you can see there, of the 4 different variables, I can isolate each one the same way that I have been rearranging formulas this whole time, right, which I won't go into detail now. But all of these kinematic formulas are important for you to know, and they all have one thing in common. None of them will tell you what the displacement is. Okay, so if the question does not give you the displacement value, you can use these formulas to figure it out. And if you have the other 3, you can figure out the final one so long as you rearrange it. Okay, but you can see here, none of these formulas will fit into our question. The reason being is because in this case here, displacement is given, but final velocity isn't given and acceleration isn't given. So you can derive the same formulas because we know that velocity is equal to displacement over time. And so if displacement is given, there are more complicated formulas that we can use, right? So in this case here, the same formula can be derived using both the acceleration formula and the velocity formula that you've used before to figure it out. So in this case here, if we have x and we have no acceleration, then we can calculate by using this formula x equals to vf minus vo divided by 2 in brackets multiplied by the time. If we have no final velocity, but we have displacement, we can use that to calculate acceleration, right? Which is this one here, vo times t plus a half at squared. If we have no time given, but we have displacement, then we can use vf squared equals vo squared plus 2ax. Now, these are really complicated formulas, right? But if we look at the variables that are given to us, we're given vo, we're given t, we're given x, and we're asked to calculate a without vf. So the formula that we're using is the one that has no vf here, right? So we're given no vf, we're given x, vo, t, and we have to calculate a, and we can use this formula rearranged to calculate. This is the formula that we would use. Now, for the purpose of this unit though, you're not expected to do this. This is year 11 physics, and you're not expected to understand kind of how do we apply, rearrange, and calculate using this formula. What you do need to know, however, are these kinematic formulas here. You will need to know the specific kinematic formulas and calculating each one of these variables given the other three. You are not expected to calculate these ones here, right? I'm simply putting this slide here to show you the complexity of acceleration because it involves not 3 variables like your velocity formula has, but it involves 5 variables, and that makes it a lot more complicated if you don't have real world results given to you. So this is a real problem that, for example, when cars need to car accidents need to be analyzed, right? They often know the initial velocity for for most purposes, like for example the speed that the object was traveling at. They're given distance, and they're not given a final velocity for the car, and so they have to try and calculate that and how the accidents come about, right? So for the sake of today, you really are just applying these 4 formulas. So you need to know these 3 formulas in addition to these 4 here as well, because these formulas will help you figure out the rest of the variables. So here are four questions that I want you to have a go. So you can pause the video using the 5 formulas and see if you can try and calculate which one is which. Okay. All right. Let's take a look at the first question. So you are given a cyclist accelerates from 0 meters per second to 8 meters per second in 3 seconds. What is the acceleration? Okay, so in this case here, you've got initial velocity, which is 0, final velocity, which is 8, time is 3. So let's use not these formulas here, let's use the other set of formulas to calculate. Okay, what I find really useful is you actually should write down the information you have first, with the right notations, with the right pronumerals, and then you figure out what you need to calculate. Okay, so you can see here, you're given the initial velocity, so that's VO is 0. You're given the final velocity, VF, which is 8, and then you're given time, which is 3 seconds. And then you want to figure out, okay, which formula do I need to use? So looking at your 4 formulas, the one that is most suitable will be the first one, which is A equals to VF minus VO divided by T. Yeah, you punch your numbers in. A would equal to 8 minus 0 divided by 3. Now, when you do this in your calculator, make sure you do 8 minus 0, you hit the enter first, and then you divide the answer by 3. Because if you do 8 minus 0 and then divide it by 3, your calculator will immediately calculate 0 divided by 3, which is 0, and then you'll get a really incorrect number. Right? So in this case here, if I did it correctly in my calculator, it should give me 2.67 meters per second squared. Okay? So that is using the first formula. Question 2. If a Ferrari with an initial velocity, so it's cruising just a little bit at 10 meters per second, accelerates at a rate of 50 meters per second squared for 3 seconds, what would the final velocity be? So now you are given the initial velocity, which is 10 meters per second. You are given the acceleration, 50 meters per second squared, and you're given time, which is 3 seconds, and you have to calculate the final velocity. So VO is 10, A is 50, and T is 3. So I will be using the VF formula to calculate the final velocity. Yeah, so I punch my numbers in, 10 plus 50 times 3, so you're going to get this final value first, which will give me VF would equal to be 160 meters per second, which is really fast for a car. Okay, 160 meters per second. Okay, question 3. A car moves from rest to 100 kilometers per hour. If the car's average acceleration is 5 meters per second squared, how long will it take to reach its final velocity? So once again, you write down the values that you do have, and then you pick the right formula that you're going to use. So in this case here, right, the question is asking how long, which means you are looking for time. So I'm going to find out what my information is, right? So I am given VO, which is 100, which is 0. It's resting. VF, which is 100, and then A, which is equal to 5 meters per second squared. Now, how long, which is T, would it take to reach its final velocity? So I'm going to punch my formula in, and then I'm going to use the T formula to calculate this. I've just noticed a mistake that I've actually made. So before I calculate, I realized that I wrote 100 kilometers per hour. So before you do that, you actually have to divide the 100 by 3.6, okay? So you probably should do that first. So in this case here, I'm going to replace 100 with 100 divided by 3.6, which will be probably about 27 point something, 27.7, okay? So T would equal to VF, which is 27 minus 0 divided by 5, which should give me a little bit over 5.5, a little under 5.5 seconds. So the answer here is actually incorrect. It's not 20 seconds, it's about 5.5 seconds, okay? Now, last question. During the last stretch of a race, a marathon runner accelerates at a rate of 2 meters per second squared for 3 seconds to reach a final velocity of 10 meters per second. What was the runner's initial velocity? So once again, what's the question asking for? Well, what is the runner's initial velocity? So it's looking for the initial velocity, or VO. So we're going to use the VO formula. We're going to punch in what we have available. So it tells us that the final velocity is 10 meters per second. So he was at the end of the race. His final velocity was 10 meters per second, right? He accelerates at 2 meters per second squared. So A will be equal to, and then he does that for 3 seconds, right? So final velocity, initial velocity is equal to final velocity minus AT. So initial velocity would equal to 10 minus 2 times 3, which equals 6. So 10 minus 6 would equal to 4 meters per second. So what it's saying is that the runner was running initially at 4 meters per second, which is really slow, right? And he accelerates to 10 meters per second at a rate of 2 meters per second every second for 3 seconds, okay? All right, so that's acceleration. My expectation is that you guys are able to use these 3 formulas and the 5 formulas quite confidently. I don't expect you to know the other formulas, but I just wanted to point that out to show you how complex acceleration actually is, okay? All right, thanks guys.